he had like tens of fractures, but I guess when you are young, you recover easily. So he's fine. So anyway, for the test, for example, here you have a Ferris wheel, and you see that at the top, first of all, the normal force always goes from the surface to the body you are interested in. So if the body is the person, the normal force goes from the seat to the person, and then you have the weight. But because the acceleration is toward the center, the largest force has to be toward the center. The largest force has the same direction as the acceleration. So that's why it's good to take the positive direction in the same direction as the acceleration. So we talk about that, right? So here you're going to have the opposite here at the bottom. The normal force has to be larger because it needs to provide that acceleration. It needs to provide the centripetal acceleration. One has to win. If there is no winner, there is no acceleration. If the net force is zero, there is no acceleration. Okay, so this is one situation. The other situation is this one. So in this situation, you see the normal force goes from the surface to the car, if the car is your system of interest, and then you have the weight, and then you can see that if there is no more contact, there is no more normal force. So in that case, you can find what's going to be the minimum speed if you want to make it and not go off tangent along a projectile motion. Okay, and I saw a video here online, and if you happen to fall in a well, that you remember your physics here, and here you have to go faster and faster and faster and faster and faster, and you see you can make it. Now the normal force here is providing the centripetal force, right? So you need a lot of muscles, of course, a lot of power to achieve that. But I found that very cool. So if you happen to fall in a sinkhole in Florida, which happens a lot, you will know what to do. Okay, so definitively this we already discussed. You see, a force is an acceleration. Acceleration means a net force. So this acceleration has two components. It has a perpendicular component, perpendicular to the velocity. So that will be your centripetal acceleration that makes the turn happen. Okay, it doesn't change the speed, but it makes the change in direction. That component here, you see, it's opposing the velocity, so it's going to slow down the car. So the car is slowing down and turning at the same time. Each component has a different job. The velocity is always tangent to the trajectory. Okay, so example application here, that will be Kepler's second law. So Kepler's first law says that you see here you have the what's it called? Halley comet, but any planet going around the sun or any comet, they will go along an ellipse, which in that case, the velocity, the speed will change with time. Okay, the velocity will change with time, and it goes like this: very fast, and then very slow, and then very fast and very slow. Because here, not only the force due to gravity will be stronger because the comet will be closer, but it has a component along the velocity. Okay, so it has two components. So 1986, you see the window during which you can watch the comet is very small. Last time it was 1996. Next time will be 2064, so I won't be around. Hopefully you will. So, but you see here, let's see if I do the force. So there is the force due to gravity here. So that force here has two components. It has a perpendicular component that make it turn, and it has a tangent component here. So this is tangent, this is centripetal. Okay, so what's going to happen is that the comet is going to slow down. And then here it's going to be the opposite, right? You still have a force here. It has two components. One component will provide the centripetal acceleration. The other component is along the velocity. So it makes it go faster. So it's going to speed up, slow down, every 76 years it takes. Halley comet, named after Edmund Halley, the only friend of Newton, so they say. Okay, we already discussed that. Tides. So I heard this now is the king tide. So tides happen because the moon is pulling. It's pulling on us. That's one explanation. When the moon, earth, and sun are aligned, and that happens for the full moon and the new moon. It happens twice a month. We have very high tides, spring tides and neap tides. In addition to that, when that happens and the moon is very close to us, we have the king tide, which can be a disaster in Florida. And you will agree, right? So, for example, you see here the ocean is being pulled by gravity from the moon and gravity from the sun. You also have some centripetal acceleration involved. I don't want to go into too much details. So you see, you have the Earth and the Moon. It's more like a binary system, double planet, and they are orbiting their center of mass. So let's say the center of mass is here. For Moon, Earth, the center of mass is inside the Earth, but you have a center of mass. So they both orbit their center of mass, meaning the Earth is wobbling because of the Moon. So it does something like this, right? So the Earth, from its perspective, it's going to feel a centrifugal force, like something pushing in this direction. So here, you have the centripetal force winning. You also have gravity, but the centripetal force will be larger. On this side, that will be gravity winning. So that's why we have two tides on both sides, right? So you see the system is orbiting the center of mass here. So there is a centripetal force from the Earth perspective acting on the Earth, pushing the ocean on this side. But here you have gravity larger. Okay, so if you want, you can take the time and see what's going on. But that's interesting. So when the three of them align, that happens twice a month. We have high tides. They are called spring tides. Nothing to do with spring. That's how they are called. And neap tide. And in Florida, it's more like even worse because we are on water, right? And king tides. We have king tides right now. Okay. Any question? No question? Good. Let's move. Next chapter. Next unit is about work and energy. Okay, I have extended the homework for tonight. For yesterday, it's tonight. Any question? We good? Okay, so I want to introduce a new physical quantity. It's called work. So work in physics doesn't have the same meaning as in the real life. Okay, work means energy in transfer. So it's a physical quantity, is a scalar, so it has no direction. It's not like a force, it's a scalar, and the unit is joule. So it's energy in transfer. So if you take chemistry, you learn about heat. Heat is also energy in transfer. In transfer between what and what? From one system to another system. Okay? So when there is work done by system 1 to the system 2, the kinetic energy will change. That's how you know if work is done. Okay, work is done by a system on the other one. If that system here wants to change the speed, okay, the kinetic energy of the other system. So let me take you, like the most important in physics is to understand the concept, and then it's just stupid math. So let's say you are pushing, you know, those red, has to be red wagon. So you're pushing here. Okay, so you are applying a force, right? That will be the force applied. So what's happening here, you are burning energy, okay? You are burning fuel, and you are transferring energy from you to this system here. And the work is done only if the work that you are doing make it move or wants to make it move. It depends if you have work opposing it over a displacement. I'm going to call that displacement delta R. So in that case, that displacement is just delta X in 1D, but it could be that we work in 2D or 3D. So remember, R is a vector, it has a X component, or delta R has a X component and a Y component. So I'm going to use delta R. Okay, so I can say the work done, it's always from something, so U on the wagon, okay, that will be how much energy is being transferred. By definition, it's going to be the force applied, okay, but that force, okay, I'm going to write down the definition. The force applied dot delta R. So if you apply a force over a distance, during the time you are pushing, the energy, kinetic energy will change. If the energy, kinetic energy, the speed does not change, there is no work done. That dot product here, that dot product, it's called a dot product, is a scalar product, okay? There is a video in Dropbox, so if you have to take calculus, like vector calculus, you need to know about it. I invite you to watch that video. That just means the following: the work done by you on the wagon, okay, will be equals to the component parallel to the displacement times the displacement. Because if instead of pushing in this direction, I push this way, I pull. Okay, let's say now the force is this way, so I'm pulling. Okay, so then only the component parallel to the displacement is providing the work. This component here is just lifting up, but it doesn't help changing the speed. Work is done only if the force can change the speed. So the dot product is just a mathematical way. It's a tool. We use mathematical tool to make sure that, so here it just means the component parallel to the displacement. Do you agree? So in that case, the work done, okay, I should take here, the work done by you on the wagon, it's going to be positive work, meaning you are increasing the state of energy. The wagon will move faster. So we say positive work. In chemistry, they do the opposite. They have to say, oh no, we are smarter than physics. Right? They do everything upside down. So they will say it's negative work, but no, physics is positive work. And it makes sense because we are increasing the energy level. Okay? So don't be confused with chemistry. They have a different formalism. Now, if you have kinetic friction, let's say you have kinetic friction, that kinetic friction is taking energy away. So there is a transfer of energy from the wagon here to the ground. Okay, so it means the ground it's going to get hotter, it's going to be warm, has to go somewhere. Maybe it will make some noise. Maybe it's going to damage the ground. All that is a consequence of that energy being transferred. So the work done, okay, by friction on the wagon, it's going to be negative. So if I use only magnitude, so first of all, if I use the formalism, so it's going to be the kinetic friction dot delta R, okay? So just a formalism. So that work, okay, will be minus, so forget about the minus here, it will be included in the dot. So it's going to be the kinetic friction in magnitude times the displacement. And this here is parallel, okay? It's parallel to the displacement in this case. Otherwise, you have to find the parallel component, okay? So work done, it's from 1 to 2, okay? It will be the force applied, and the force has to be parallel to whatever displacement. So if you move a wagon in, I don't know what, in 2D, like if you push here, have a wagon here, you pull, you need to, and that will be your delta R, you need to find the parallel component to delta R. Only the parallel component is doing work. Okay? Once you understand that, that's it, we are done with the unit. And then it's just details. So we're going to see that energy is the ability to do work. If there is energy, then you can transfer some of that energy to another system. One way to look at it is that if something has energy, it can break, can do damage. Okay. Units is joule in the SI system. So Newton force times displacement, Newton meter. You have other unit of energy, erg. Erg is very small. It's like a push-up by a fly. You know, fly, they do push-up. So that will be 1 erg. And then you have calorie. So that will be the chemistry calorie with a lower case, 4 joule. And you have the food calorie with the uppercase C, which is 4,000, so 1,000 times more, because they don't want us to realize how much energy you have in a cookie, for example. Like when they say 150 calorie, you say, oh, but 150 is not that much, but that will be 150,000 times 4 joules, lots of calories. Another unit for energy is the kilowatt hour. Kilowatt is for power. Power is energy per unit time. Then you multiply by the time and you get energy. Kilowatt hour. And then English, forget about them. BTU, they are still using that. Forms of energy. So you have kinetic energy. We're going to focus on that. Energy of motion. It's going to be proportional to the mass and to the speed square. That's why it's a killer. If you multiply the speed by 3, kinetic energy will be multiplied by 9. So don't go drive too fast. And then you have potential energy. So potential energy is stored energy because of a configuration. So for example, I have potential energy relative to the Earth, depending on the distance, right? It depends on the configuration. So it has potential energy. So this has potential energy. So it stores energy inside the gravitational field. If I let go, it goes to kinetic energy. So I can get back the potential energy, right? So it stores potential energy. With potential energy, you always have a restoring force, a force that wants to bring back the system to a lower level of energy. Now if I have, see, when I do this, right, that's called elastic potential energy because of its configuration. I'm storing energy and I can let go, right? So it just store energy. You can store energy in the molecules. That's how we produce ATP. You know, when you are producing ATP, it's actually potential energy being released. You can store energy in the nucleus, like atoms. That's the atomic energy. So it's because of the configuration inside the nucleus, and then you can break this configuration, and you're releasing the atomic energy. You have energy from radiation, so from the sun, so it's called radiative energy. For example, the UV light has energy because you can become very tan, right? That's from the UV light, so you have radiation. And then you can go from one to another. So all the energy that we have to go biking, it's from the sun, because of the sun, that energy here will be stored in potential energy in the flower, and then the cow eats the flower and you eat the cow, so you are eating sun energy, right? It's really unless you are a vegetarian, so you eat the flower. Okay, so all the source for energy on earth is the sun. So anyway, kinetic energy, very easy. You know, you can relax now. It's much more easier. 1/2 mv square, easy to understand. It depends on the mass and the speed square. So Newton didn't understand kinetic energy. He understood momentum, not kinetic energy. Other scientists did after him. So then you're gonna say a work done when energy is transferred from one system to another one, there will be a change in kinetic energy. So this is called the work energy theorem. The net work, so the net energy transferred to a system will translate as a change in kinetic energy. If the network is zero, then there is no change in speed. Remember change. What does that mean? Change, it means final minus initial. Okay, so when you do the change in kinetic energy, you factor out 1/2 times the mass, and then you have final square minus initial square. Don't do the typical mistake to do final minus initial and then you square. No, final square minus initial square. Okay? On the highway, if you multiply the distance by 2, your kinetic energy is multiplied by 4. So you need 4 times the distance with the car in front of you. Otherwise, you multiply by 4 the damage. Okay, so let's do super easy, extra easy example. Did I skip? I skip. Okay. Okay, let's do the example and I come back to the math. I just skipped. By accident. It's an accident. I'm sorry. Okay, let's do an easy one so you get the idea, the concept, and then we go back to the math. And by the way, that will be chapter 1 of your book, where they go over the dot product and the cross product. For now, we worry about the cross product, scalar. Okay, so you see here, initial speed is 5 meters per second. Final speed is 0. What's going to be the change in kinetic energy? So kinetic energy is 1/2 mv squared. So the change, I'm going to break it down. So it's the final minus the initial. Okay, so that's very easy. So 0.5 times the mass, final minus initial. So you can factor out. Final is 0. And the mass is 50 kilograms. Okay, Okay, so you get the final velocity is 5, so 5 square, enter, times 50, enter, times 0.5, enter. Do it, do it, do it, do it. Everyone do it. Yes, very good. Negative 625 joules. Yes? All agree? Okay, so this is easy, right? For a change, right? It's good. We go from complicated. So kinetic energy is 10 meter per second. Okay, so it's going to be 0.545 10 square. Do it, everyone. If you don't have a calculator, download one. Do you do it? More you do, less easier it will be for the assignment. It's gonna be, yeah, joules. And the one, now if you go at 5 meter per second, so it decreases by a factor of 2, kinetic energy will decrease by a factor of So when they ask you what's the ratio, that means what's the factor, and you say the initial one over the final one. Okay, it's going to be 2250 over 562.5. You're going to find 4. Exactly. So this is a killer, okay? Kinetic, you have to understand that kinetic energy is a killer. It kills you. Because if you change your speed by a factor of 3, you go from 30 miles per hour to 90 miles per hour, and the kinetic energy is multiplied by 9, and there is a crash, you have 9 times more destruction. It's very destructive. Very, very destructive. It killed the dinosaurs, right? The meteorite. Okay, it was so big, 10 kilometers in radius, so it could not be destroyed by the atmosphere. It hit the earth. So all that energy, okay, turned into kinetic energy, and all that kinetic energy turned into heating up the earth. You had fires everywhere, brought the earth to a boil, killed the dinosaur, which is good for us, right? We don't want to have a T-Rex, we have to wait for the T-Rex to go. But very destructive. Okay, so don't go too fast on the highway. We have enough crazy people. Okay, just the parenthesis for the math. Okay, so you have two vectors, A and B. Okay, you dot them. When you're going to dot them, you get a scalar. If you cross them, you're going to get another vector. So if you dot them, you get a scalar. Okay, that quantity is going to tell you how much A and B are aligned with each other. If they are parallel to each other, the cosine here will be equals to 1. Okay, so they are parallel in the same direction. If they are anti-parallel, they are still aligned, but the cosine will be equals to -1. What's happening if they are perpendicular to each other? 90 degrees, so cosine will be 0. Okay, so that way you can find, how much aligned are two vectors. So what you are doing here, you multiply the magnitude of the magnitude of A times the component of B along A. Okay, so here, for example, you have A and B. If you dot them, okay, you're gonna have the component of B along A times the magnitude of A. So it's a way to this here you can say, that's what I told you before, you can say, or the opposite, right? So you can say that will be parallel along A. So this will be the component of B parallel to the direction of A. Or you can do A parallel to the direction of B. It's going to be the same thing. Okay? So for example, work is by definition, okay, it's going to be the component of F parallel to the displacement times the displacement. That's a dot product or scalar. Okay, so how are we going to apply that to physics? Let's say something is moving in this direction and there's a force here perpendicular to the displacement. What's going to be the dot product? They are perpendicular to each other. Cosine 90, it's going to be 0. There is no work done. Why? Because this force here is not helping in making it go faster or slower. It has no influence on the speed. The work done is 0, and we just use a mathematical tool to translate this idea. Okay, now here it's anti-parallel. So the cosine will be equals to -1. That force here is doing negative work because it's taking away the energy. Okay, it's slowing it down. It does change energy, kinetic energy. So yes, there is work, but it's a negative work because it's trying to make it go slower. So this one, the cosine equals 1. Very good, right? So 1. So it means it's positive and it will be the maximum work you can harvest from the force applied. Okay, the maximum work. If it makes an angle, then you have to use the cosine because the force has two components. The perpendicular one doesn't do any work, only the parallel one is doing work. Okay, so that's the concept. To express those concepts mathematically, so we need a tool. That tool will be the dot product. Okay, so now there is another definition. So you have two definitions for the scalar product, the dot product. Either you say it's magnitude of A times magnitude of B times the cosine of the angle between A and B, or you can use the components. So you say the dot product will be x component of A times x component of B plus y component of A times y component of B plus z component times the z component of B. Okay? So you have two ways to do it, and in geometry they use that a lot to find the angle between, I don't know, two in space, two segments. So, okay, so let's try to do an example. So this is math. So let's go fast because I don't like math so much. So we're going to use the first definition first, right? So A dot B equals x components. You multiply the x component and then you multiply the y component. That notation, we already seen this notation. It's the unit vector, just mean the x component is 2, the y component is 3. The other one means x component is -1, y component is 2. when you dot them, okay, you're gonna get 1, you sure? 2, you multiply the component, right? So 2 times minus 1 plus 3 times 2, which is 4. 4, right? It's going to be 4. Okay, it's positive. That will be the dot product of two vectors here. You can even do it geometrically. Okay, no, I mean you can see what is that? 2 and 3. 1, 2, 1, 2, 3. So you have 2 and 3, and the other one is minus 1, 1, 2. So you have one vector here, vector A, not vector A, and this is vector B. And that will be, you have an angle here between them. And then they ask you find the angle between the two vectors. So in that case, you use the other definition, AB equals magnitude of A times magnitude of B times the cosine. And you know that the scalar, the dot product equals to 4. Okay? By definition, you have two definitions. You can use this one, or you can use A times B times the cosine. So you have two definitions. Okay, so do it. Magnitude of A, you're going to use Pythagorean theorem. 3 fois 3, 9 10 to 13 times 2 and 4 plus 1 is 5. Cosine theta equals 4. You do it. This is about 8. So cosine is 4 divided by 8, which is 1/2. So the angle is about 60 degrees. And if you like math, you didn't have to do that. Okay, you can find the tangent here. You can find this angle here, and then you can find that angle here using the tangent, and then you can do 180 minus this angle plus that angle, you get this angle. So you can use trigonometry. Remember, for test 2, you still have one question about vector. I forgot what it is. Like adding vectors, you need to know how to add vectors. Any question? So this is an introduction to your calculus class. Vector calculus is easier than calculus 2 with the series. Series is very challenging. Okay, so you see here, it's in your textbook is unit 1, chapter 1, they go over the math. And in Dropbox, I have placed 2 videos. One video goes 3 videos, one about vector, 4 videos, one about vector, another one about vector, adding vector, one about dot, and one about cross. So you can apply this principle to thermodynamics, okay? So if you are pushing here, so this is a gas, for example, like you can do that with a tire that or inflating a tire of a bike. So if you push, and you prevent the air to escape, you touch, it's going to be warmer because you are doing work. You are applying a force over a distance, so you are transferring energy to the system that goes into kinetic energy. Kinetic energy of what? Of the gas molecules. And by definition, temperature, the temperature definition of temperature is the average kinetic energy of the molecules per molecule. So you are increasing the gas here, the molecules are going to move faster, which translate as hotter, right? The temperature will increase. So you are doing work on the system. Thermodynamics is very challenging, in my opinion, the advanced class. So energy, okay, we did that. Okay, let's take a very simple example. You are pulling here, and what's going to be the work done on the box by you? The displacement is 10. So are you, which one you're going to use? Sure. The 30, right? It has to be the parallel component. You have to dot the force and the displacement, or you just remember we want the parallel component. This one is not doing work. It doesn't help changing the speed. So the work done will be just 30 times 10, which is 300 joules. Okay. Work is negative, that means energy, kinetic energy, is removed from the system. Work is positive, energy, kinetic energy is added to the system. Okay, so here you have two ways to do it. We need to find the change in kinetic energy, we need to find the net work. The network, right? Because you have a force, each force will change the kinetic energy. So we need to find the net force. Okay, we're gonna make him happy. I don't like when people are not happy. So the net work done on a system, so that will be the crate, you can say it's the net force times the displacement. That's one way. Or you can say it's the sum of all the individual work done on the crate. Okay, so you have two ways to do it. So if I go with this definition here, so the work done by you on the crate, it's going to be what? So 100, yes, times 10, so it's going to be 1,000 joules. So energy is transferred from ATP to the muscles and from the muscles to the crate. And then there is work done by friction on the crate. So it's going to be minus 50 times 10. So that will be minus 500 joules. Exactly. So then you can find the net work done on the crate. That will be 500 joules. And that will be that net work that will be equals to the change in kinetic energy. So that will be for this definition here. Now, if you can also do what you can do this one. So the net work will be the net force times the displacement delta x. I don't have to worry about dot because they are parallel. The net force is 100 to the right minus left, which is 50. Okay? So the net work will be 50 times 10 and it's going to give you the same thing. Okay, so you have two ways to do it, right? Either you do the sum of the individual work or the network times the displacement. Yes, yes, yes. Okay, so it's good to start with when you learn something, like for anything, start with very, very basic examples to understand the concept, and then you can paper and solve the math. Yes. It depends along the displacement. You take the component of the forces along the displacement. It doesn't have to be x. It depends where is your displacement.
Take it along with y.
Yeah, so if you are lifting, exactly, if lifting, you take along the y. It depends on the displacement. So if you are, as I said, like, so if you have a train here moving and you have a thrust, the train has a thrust, I know it goes this way. So that will be your displacement here. But if the force is that way, okay, someone is pushing this on the railroad, so push this way, only the parallel component along the displacement will matter. So only the parallel component, the component along the displacement. Displacement doesn't have to be 1D. Displacement can be 2D. So if displacement is 2D, then you have to work along the X and along the Y. If it's moving this way, you want to find the component along that displacement. Okay, so let's try to do this one. This one comes from an algebra book, but it's nice. Make sure to do your textbook as well, because it will take you to another level. Okay, some of their problems are interesting, and it doesn't matter the publication. It's always they take the same solved problem. They don't bother making up new solved problem. They just shuffle the questions at the end, so to make you buy new publication, which is understandable. They have to make money, but it's the same solved problem. So acceleration is 1.5 meter per second. So you see here they are focusing on the crate, only on the crate. So it means that your bag, imaginary bag, it's going to be this crate here. On the crate, you always define your system. The system is the crate. The crate does not slip. So it means it's static friction. So when you have two surfaces in contact and it doesn't slip, static friction. If there is an acceleration this way, that means you need to have a force here. Okay? The acceleration is the same direction as the force here. So that will be the static friction. It has to be this way. Okay? There is some hooking. They hooks together. Same direction. That's the only force applied. And of course, here you have the normal force and you have the weight. And it's moving in this direction. So first of all, is the normal force doing work? No. Okay, I'm going to call that delta x. That will be your displacement. No work. Okay, so the work done by the normal force equals 0. Is the weight doing any work? No. Right? It doesn't help making motion forward. It's no work. It's perpendicular to the displacement. And you see that the only work done is by the static friction. So the work done by the static friction on the crate, in that case, it's going to be positive because it's the force that makes it move forward relative to someone watching here, for example. So it's going to be the static friction here times the displacement. We don't have static friction, but we have the acceleration. Yes, very good. Very good. So if I look at this one, just the crate, I'm going to apply Newton's second law to the crate. So I'm going to say the static friction or the force or the thrust or the driver equals the mass times acceleration. So you apply Newton's second law to the crate. Which is 120 times 1.5, 180 Newton. So now I have the force providing the acceleration. Okay? It's algebraically it's easy. Conceptually, not that easy. You really have to understand what's going on. If something is accelerating, that means there is a net force. That net force has to be in the same direction as the acceleration. You have to focus on the crate because they talk about the crate, they don't talk about the truck. Okay, so the work done by the force here on the crate is just going to be the force times the displacement, which is 65, which is joules. Did you get that? The unit is Newton meters, but it's joules. Joules is Newton times meter. And Newton is kilogram meter per second per second. Boom, boom. They take shortcut. Question? Okay, once you understand the concept, it's not that hard. Okay, so they do it step by step, blah, blah, blah. Or they use scientific notation here. Yeah, and they take in account significant values, so they round. Okay, so if you walk here with a suitcase in your hand, but you are moving at a constant speed. So I walk here. So my displacement is this way. Am I doing work on the back? No, because I don't make it go faster. I have to run. So if I start to run, the back stay behind and it's going to catch up, right? So there is no work done, even though I'm puffing and huffing and it's very heavy. I'm not doing work on the back. I'm doing work on the environment, right? Because I'm sweating, it's very hot. The molecules are moving faster, but I'm not doing work on the back. Okay, so typical conceptual question, if you are taking the MCAT, they love those questions, right? Are you doing work on the suitcase? No. Even though you are tired. So that's why in physics, it doesn't have the same meaning. Doing work means changing the speed. If you don't change the speed, if you are moving if the suitcase is not going faster or slower, then you are not doing work on it. You are doing work on molecules around you. So it's not that easy. So we did this one. Okay, let's try to do this one because it's a interesting one. Okay, not this one. So I have to be careful here because it's a review of kinetic friction. Okay, kinetic friction is the coefficient times the normal force. Normal force is how hard surfaces are pulled together, how hard it's being pushed. In that case, you are lifting, so it's not the weight. The normal force is not the weight. Okay, so to help each other, talk to each other. So we need so that way we review, because we need to find the kinetic friction. Kinetic friction is the coefficient times the normal force, so you need to find the normal force. Okay, so you can help each other. Okay, try to do it. Don't stare. Do it. So you see how much work is done on the crate. So the net work done on the crate. So you need to find the work done by the pull and the work done by friction. And then you add them up. Or you can find the net force and then you multiply by the displacement. Okay, so do it. So we're gonna say you are an Eskimo on the sled. It would be the force. Okay, so this one is easy. So 120 times, which component do I need? X component, very good, because here it has a Y component. I'm gonna say perpendicular or Y, let's call it Y, and it has a Y component. Only the X component is helping with the change of speed, so it's going to be a cosine 30, and don't forget to multiply by 5. So this one is easy. Again, 520 joules. So that will be the work done by you on the sled. Okay, do it. So then we need to find the friction, which is negative, right? It's going to be the kinetic friction times 5. And now we have to go back to the previous unit, because we need to find the frictional force. By definition, the frictional force is the coefficient times the normal force. And normal means how hard they are pushed together, right? So how do we find the normal? We see it's an equilibrium up and down. So we're going to say everything up equals everything down. So if you have not done it, do it. Find the normal. Everything up, you have the normal up, and you have the Y component. Yes. Because this is what I have explained. When you find the work done, you take only the component parallel to this displacement, because only this component changes the speed. It's the definition of work. It's a dot product, right? Dot delta x, right? So it's going to be F cosine theta delta x. That will be the angle between F and delta x. So either you take the mathematical definition of the dot product, or you say, I need to find the component parallel to the displacement, because only this component will make it go faster or slower. That's a definition of work, right? So you can say the work is the parallel component. Parallel to what? Parallel to the displacement. That's a mathematical definition. Or you have to say only the component that make the speed change. This component is making it go forward. That component is lifting up. It does not help making forward motion. Okay, so along the y-axis, everything up equals everything down. So we have the y component, which is 120. Here is your y component, plus the normal force equals 500. Okay, so that's from last unit. So the normal force equals this is 0.5, so that will be 60. So 500 minus 60 is 440 joules, right? If you take the MCAT, you need to know that in your head. You don't use the calculator, okay? They expect you to know that sine 630 is 0.5. You have to memorize the simple 45, 30, and 60. Okay, so we have the normal force. Once we have the normal force, we can find the frictional force. So Fk equals the coefficient times 4, 0. Is that right? Which is 44 joules. So we can find the work done here. So minus 44 times 5. Okay, so the work done will be minus whatever, 220. Okay, so negative work by friction, positive work by the applied force. Then you can find the net work. So 300 joules. So once you have the net force, then you know the change in kinetic energy. Maybe you find this one too hard to do it step by step this way. So you can also do instead the net work is the net force dot the displacement. So you need to find the net force along the x times the displacement along the x. Okay, so you can say that will be your x component here minus your kinetic friction times your displacement, because you want the parallel component. So you can do it this way if it's easier. Different people have different mind. I don't know. Any question? So you go step by step. Yes.
440.
440.
How'd you get the 440?
Ah, here.
I understand up to the 5.
Okay, so normal force is, so this is 60. So it's going to be 500 minus 60.
We do that because of
Because we need the normal force to find the friction. That's from the last unit. So you need to find the kinetic friction, you need to find the normal force. And normal force, you find it by saying everything up equals everything down, because the normal force is not equal to the weight, because you are lifting. So they don't squeeze as much. Okay, so everything up equals everything down. The only unbalanced force is the component here. The x component is providing the acceleration. Acceleration means change in speed. Change in speed means that there is work done. Work done is a transfer of energy. You have a positive transfer from the Eskimo, negative transfer from the friction, taking away energy. Okay? Yes. Yes. Yes, thank you. Newton. Thank you. Question? Good. Okay, so this comes from calculus-based book. It's more advanced math. Yeah, benching. Okay, so here is just conceptual. When you are lifting at a constant speed, lifting the what is called dumbbell. Okay, lifting up. Are you doing positive work or negative work? Positive. Why? Because the force here has the same direction as the displacement. You are trying to make it go faster. So what is doing negative work? Very good, gravity, right? So that's why the net force is zero. Okay, so there is no net force. You are doing work against gravity. Now, when you lower down, now you are doing positive work or negative work? Negative, because the force and the displacement have opposite directions. So you are trying to slow it down so it doesn't crush you, right? And gravity is trying to do positive work. You're always doing against gravity. It's very dangerous here because that's why they say not to do it if you don't have people around. People have died from that, right? It depends how much you lift. Negative work. So because what is it trying to do? If there is no gravity, you will accelerate. So if your effect is to accelerate, that will be positive work. If your effect is to try to slow down, that will be negative work. So here you are trying to increase kinetic energy, that will be positive work. Here you are decreasing kinetic energy. If gravity was not there, that's negative work. So gravity here, yes, if gravity was not there, it will speed up. If gravity was not here, it will slow down. The network is zero because of gravity. It's always doing against you. Okay, you are doing work against gravity. Okay? Which is good. If gravity was not here, we will all have osteoporosis. Right? Like those astronauts that were left for 9 months, whatever. Terrible. You need gravity for your bones. I guess we evolved with gravity, that's why. I don't know. Okay, tangent. Let's go back. So this is called work kinetic energy theorem. The net work equals to the change in kinetic energy. Okay? And now you see where that kinetic equation comes from. You see, remember v final square minus v0 square equals 2 times acceleration times delta x. Okay, now let's develop a little bit algebraically. You multiply by 1/2 the mass everywhere. Okay, you get this, and then you're gonna get that, and ma is the force, and then you have delta x. So it comes from here. That is the work theorem, energy theorem. The change in kinetic energy is the work done by a force, or the net force. That will be the net force. Remember, in this equation, it was a constant acceleration because there was a constant net force. So it comes from there. Okay, that is easy. We already done that. Did that, done that. So friction, okay, that's easy. That's easy too, it's just scientific notation. Okay, let's do it in our head. So a force of 50 Newton and 100 Newton and 50 for the friction. What will be the net force? 50, right? So I'm going to do it this way. So the net force is 50 Newton and it's along the motion, so I don't have to worry about the angle. So the net work will be 50 times 10, which is 500 joules. According to the theorem, that will be equals to the change in kinetic energy. So the 500 joule equals to 1/2 the mass, which is 50, final speed minus initial speed. You can do that too with kinematics, right? The final square equals initial plus 2 times a delta x. It's the same equation. This is the net force divided by the mass. It's the same equation. Okay, so then they say initial velocity is 0, so this is 0. Okay, so you have 1000 divided by 50 equals final square, and you can solve 20. 4.5. Okay, so some of the problem is just math. They will give you initial velocity and they will ask you find the final velocity. So you just do it algebraically. Or you can always use this one, kinematics, with the net force. Net force divided by the mass is the acceleration. Question? Okay, so this one is another example. What is its final velocity? So I'm just lay out the equation. I'm not going to, because it's just algebra, right? But just lay out algebraically. Do it. Okay, so force 0.056 times the displacement, so 2.42 times 10 to the 9 equals the change in kinetic energy. So 0.5 times 474, final speed idk minus initial speed vk. Except I don't have enough space. Okay. So 0.056 times 2.42 times 10 to the 9, 0.5 times the mass, final speed idk, initial speed, yes. And this is v square minus 275 square. And then it's just algebra. Okay, I'm not going to do it because math takes over. Okay, you do this times that, enter divided by 0.5, enter divided by 474, enter plus 275 square, enter, and then you take the square root.
Like 800 forward.
Okay, let's see. Yes, 800 something meter per second. Okay? Okay, so this one comes from your book. You have to buckle up. This one is a little bit challenging. It makes sense for engineers, right? It means you use, let's say you can think of that as using potential energy. That potential energy goes into kinetic energy. That kinetic energy goes into applying a huge force over a small distance. Because there is always a trade-off between distance and force. So it means this is a small force, the weight, small, big distance. So it's like conservation of energy. So small weight, quote unquote, times a large distance equals to small distance, because it's not going to go into the ground by much, times huge force. So it's a trade-off between force and distance. Work is energy, energy is transferred, energy is conserved. Except that you're going to lose energy to friction. Right? So if you have like a, this is a hammer. Okay, I hope that you can see that this is a hammer. And this is a nail. So you're gonna have, and let's say I'm very weak. I have no force here. So very small force here that I'm gonna apply. So I'm gonna have a very small force times a huge distance will be equals to, so the nail is going to go in by a very small distance, so the force applied to the nail will be huge. That will be huge force times a tiny distance. Okay, so it's like biking. You have a trade-off between the effort and the distance, effort and speed. Now, what is the force applied? How do I know the force applied? It's just that if the nail is applied, exactly. So here you have a change in kinetic energy. That kinetic energy, the change in kinetic energy will be equals to force times distance. How do I know the force? It will be the normal force. For every reaction, you're going to have an opposite and equal reaction. The normal force will be huge. You push very hard, it's going to push back very hard. So if you can figure out the normal force, you will know what will be this huge force, right? That will be your normal force. So what kills, it's not falling, it's the landing. Because when you fall, say someone is falling here, okay? So it has a weight, the weight is not that much, the distance is really big, but when you're going to reach the ground here, what's going to happen? The distance, yes, the distance will be very, very tiny. So the normal force will be huge. That's going to kill you. So it's the landing, which is a killer, right? So if you don't land, that's fine. Okay, you'll be fine. Okay, let's start to work on this one. It's in your book, and if you have the book inside Canvas, they go step by step as well. Let's do just the beginning. So at the beginning, it's easy. And you have kinetic frictions. You have the distance, blah, blah, blah. So here that will be for after. And it has a rail. You see, you have to guide. So there is a rail. So you have frictional force. So first we need to find the speed before it hits the pole. So that's easy. So you can use the work energy theorem. So the work done by the weight. It's the weight, the force is the weight, gravity is doing positive work, and you have negative work from friction. So you can find the net work done on hammerhead. So you want to find the final speed here. So this you can do. Ah, okay, so no, it's not hard. Who said it's hard? No, the first part is not hard. No, you look at the network. You have gravity here, 2000 Newton, and you have friction here. Okay, so the network done, okay, will be the work done by gravity and the work done by friction. Okay, so the network will be equals to the work done by gravity. It's easy, it's 2000 times 3. Okay, that will be your displacement here. That's your displacement here. So it's doing positive work because it's making accelerate. And then friction is doing negative work, so 60 times 3. So the net work equals, did you get that? So the first part is easy. Gravity is helping, making it go faster. Friction is slowing it down. Or you can say the net force, there is an acceleration, so the net force times the displacement. And you have an acceleration, it's accelerating down. Okay, so the net force has to be down. Okay, so once you have found that, you see that will be the energy that this thing has before it hit. So that will be the change in kinetic energy. So that will be 0.5, the mass, final minus initial. Okay, and you solve for V final, right? So you go 5820 divided by 0.5, enter, divided by 200, enter, and then you take the square root, and what do you get? Ay, 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 ay. Huh? Do it, do it, do it. Okay, are you taking your calculator? 5820, enter, divided by 0.5, enter, divide by 200, enter. You take the square root. Huh?
7.6
Well, very good. 7.63. Yay. Final speed. Before it hits. Okay. And now that's when the headache starts, right? Because then we have the pole. The idea is to put, like you see them at the marina, sometimes they drop weight, put the pole inside. Okay, so and then you have so this is your pole inside the, like here, and here you have the hammer head. Okay, so it has a huge speed, so it's gonna hit. So what are the forces acting on this thing here when it's gonna touch? What are the forces acting on it? Gravity, very good. You have gravity, which is the 2000. What else? The normal force. Remember, acceleration is up because it's slowing down. So the normal force has to be huge. Way bigger, as you said. Exactly, way bigger. And then you have some friction. That's the most important thing to understand. Is that the normal force, it's gonna be huge. The normal force will be really the force that kills you if someone falls. It's a normal force. So the net force is actually the normal force and then minus the weight and minus kinetic friction, which is very small.
They gave me the question. They gave me the housing
That is 60, that is 2000. So what do they want? The average force the hammerhead exerts on the beam. That means find the normal force. Right? So we have 2000. We need to find the normal force. You hit something, it's going to hit you back. So we need to find the normal force, but it says here that the distance it's going to go in is 0.074. And we have the energy transfer. That energy, that kinetic energy, okay, that kinetic energy, 5, 8, 20, okay, will be equals to, it's going to go into applying a force over a very, very small distance. Yeah, so you can do that for next time. Okay, all that energy is going to do work on the pole. That will be the net force times the distance. Then you find the net force, and then you find the normal force. At the end, we can go back next time, but at the end, you're going to find that the normal force is 40 times the weight. You see, 40 times the weight. So it means when you fall, you are not going to experience your own weight. You're going to experience much more. Exactly, that's the killer. It's the ratio between the distance. Smaller the distance, harder is the force. So it's like a hammer. Okay, force times distance. It's a trade-off. Small distance, large force. Did you survive? Shall we stop? You should find, okay, I did the computation. You should find 8709 Newton. 40 times the weight. It's huge. So don't fall, okay? Be careful.